Hello, welcome to statics. We're going to cover shear and moment diagrams using the method of sections. So a little bit of a background. There are two methods to be able to draw a shear moment diagram. And as I mentioned in the previous video on internal forces, that what you want to do is kind of figure out what the external loads are basically doing to the beam or the section you're looking at internally. Now, shear moment diagrams are a great way to be able to figure out exactly what's happening throughout the entire beam. And so instead of just picking a particular section like the internal forces, where we say find the internal forces at point C, in shear moment diagrams, so you're just drawing the entire profile, and then what you're going to do is you can use that to pick particular sections of that need your critical attention. Okay, so to get started, remember that we said that if we have internal forces, that we have three things going on. We have N, V, and M, where N is your normal force, V is your shear force, and M is your moment. For shear moment diagrams, obviously, they come from the name, so we're just going to be looking at V and M. So your shear force and then your moment. Now remember that shear force is going parallel to the surface, right? If you're looking at this surface, it's going parallel to the surface. Someone mentioned that you can view it as a pair of scissors. Yes. So they go with the grain that you're looking at. And moment is either in counterclockwise or clockwise directions. For shear moment diagrams, for the method of sections, what you want to do is look at your discontinuities. So discontinuities could be your external reactions, just like what we found over here. I've gone ahead and found the reactions for you, 327.5 and 102.5. It could be external concentrated loads or moments, so 125 and 125. And then also your distributed loads. So the trick here is to make cuts before and after any of these concentrated loads and reactions. Okay, so if for a problem like this, what we're going to be doing is making a cut in here, making a cut in here, making a cut in here, and then also making a cut in here. Now, as I mentioned in the internal forces video, it really does not matter what section you pick. You can just pick left or right hand side, but what you want to do is try to be consistent in terms of how you are dealing with it. So shear moment diagrams, as I mentioned, it looks at the entire profile. So what you want to do is pick a section and find an equation that kind of takes care of the entire section that you're looking at, and I'll explain that a little bit. So over here, I'm going to change the color and call it this my A, that's my B, that's my C, and that's my D. Okay, so if you're looking at region A or cut A, so for cut A, okay, so if you're looking at cut A, you'll see that the only things that you have on there are the distributed load, which is going to be 20 pounds per foot. Okay, so when you're making a cut, as I mentioned, what you want to do is draw your shear and then your moment. Okay, and we know our distance in this case is going to be x. We'll change that to green. All right, so if you have the cut, the area that you're looking at, only this section right here, you have a 20 pound per foot and then shear and moment. So going back to a trusted sum of forces equation, you don't have to sum forces in the x because there's no shear. There's no normal force. So sum of forces in the y direction, that gives me my V equals negative 20x, where x starts from the edge of the beam and goes towards some point between 0 and 9. Okay, so it could be any point in this whole region. It really does not matter. It's just a cut that we've made. So we are saying that x, 20x defines or describes your shear. If you're summing moment about the cut, okay, so this is your cut point. If you're summing moment about the cut, now what you're going to have is M, which is positive, right? Plus 20 pounds per foot times x multiplied by the distance, which is x over 2. So this gives us my moment equal to -1. Actually, it's going to be -10. I was going to say -1 over 2 times 20, or -10x squared. All right, perfect. So for the first cut, we have v equals -20x, and then we have m equals -10x squared. Now, what I'm going to do is I'm actually going to leave these hanging for a bit, and then we'll come back and deal with them. So for the second one, we're going to make a cut around B, which is between the edge of 9 feet right here and the next one, which is 21, 9 plus 12. Okay, so if you're drawing your for cut B, what you want to do is actually take the left hand side or right hand side, which doesn't mean take a random middle, but actually take everything. Okay, so we have this is the entire distributed load, which is 20 pounds per foot. We know that we have a reaction at the edge of the distributed load, which is 327.5 pounds. And then we have our shear and our moment. Okay. So going back here, we have our distance that we know as 9 feet, but our distance in this case from the edge to where we made the cut, we're also going to call x. What we're doing once again is we're finding equations in terms of x, where x can range from anywhere from that discontinuity to the next discontinuity. And as I mentioned, we'll go through the rest of the example. All right, so summing forces in the y direction, we have -v minus 20 pounds per foot times 9 feet plus 327.5 pounds. Okay, and that gives me v equals 147.5 pounds. So you'll see that in this case, your shear doesn't actually have any x component, which tells you something. It tells you that there's some kind of consistent amount of shear going on, and we'll deal with that in just a bit. So we'll leave that out. With so summing moment about the left edge equals 0, we have m going positive, right? So m minus v times x plus 327.5 times 9 minus 20 pounds per foot times 9 feet times 1/2 that distance. That's all equal to 0. We know that v in this case is 147.5, which gives me my moment equation as -2137.5 plus 147.5x. And we're going to leave that for a second. Alright, now going back up here, we're going to make a cut between the next 12, right? So between the first 125 and the second 125. And we're going to pick the left hand side. As I mentioned earlier, it really doesn't matter which side you pick, just for consistency, we're going to go with that. Now for the last cut, we actually go over the right hand side, and I'll explain why I did that. So for cut C, this is my drawing. So for cut C, I have my 20 pounds per foot, the 327.5 reaction, and then I also have 125 pounds. Okay. Then I have V and I have M. So going back again, we're drawing. We have 9 feet, 12 feet, And then we have our x going all the way from the left edge all the way to the cut, and that's x. So summing forces in the y direction, I have negative v minus 20 times 9, which is for the distributed load, minus 125 pounds plus 327.5 pounds. And that gives me my v as 22.5 pounds from rearranging. And then if we're making a, we're summing about some point, so in this case I'm summing about the left hand side again, so the left edge, I have my m minus, if we're summing about, we have 20 pounds per foot times 9 times 9 over 2 plus 327.5 times 9 minus 125 times 9 plus 12, which is 21, minus v times x, which we know v in this case is 22.5, and that's all equal to 0. And that gives me my moment equation as 427.5 plus 22.5 x, and that's pound-foot. Okay, and then finally, going back up here, we're going to look at our last cut, which is between 125 and 102.5, the other reaction. Now, we could still do what we're doing, where we have, we pick the left-hand side, but for a change, we're actually going to pick the right-hand side. What you want to remember is that your x starts from the left edge and goes towards the right edge, which is going to be very, very important for what we're going to be doing. So if we make a cut and we're picking left-hand side, so FBD of left-hand side of cut D, now we have just this little tiny piece with your reaction, which is 102.5 pounds. Going back up here so you can see it, 102.5 pounds. And then actually that's it. So now we just have our shear, and then we have our moment. So then for the distance, we have the entire length, which is actually 45, 12 plus 12 plus 12 plus 9. So 45 minus x, and that's the distance, right? Because if you're looking over here, x will go from all the way from the left-hand edge all the way to this point, which means this distance right here is going to be 45 minus your x. Alright, so finally, summing forces in the y direction gives me v equals negative 102.5 pounds. Now, summing moment about point is what we're going to be looking at. So we could say sum of moment about the cut, and that gives me mb negative plus 102.5 times 45 minus x, and that's equal to 0. So then we have our moment equation being equal to 4612.5 minus 102.5 x. That's in pound feet. Alright, so that's a little bit of a recap. I'm actually going to section out this part because we're going to need to use this equation to be able to draw a free body diagram. So up until this point, we've not really touched the free body diagram. We've just been coming up with equations for the little sections that we've drawn, and then we're going to go back to our diagram and draw a free body diagram. Alright, now the first one is going to be your shear, and that's in pounds. And then the second one is going to be your moment, and that's in pound feet. Okay. So what you want to do is starting from the left hand side, we're going to actually start putting in our distances. So we have 9, 21, 33, and then finally at 45. And the same thing for your moment. We have 9, 21, 33. If you're wondering where that's from, just add up your distances. 9 plus 12, 21, plus 12, 33, plus 12, 45. Okay. So now going back to our main problem. So we have some ranges that we're going to deal with. So if you're looking back at the drawing, we have from 0 to 9. It's where your distributed load is being expressed. So you have at x equals 0, we look at our velocity equation, we could have v equals negative 20 times 0, which gives me 0. Okay, and then at the other extreme, I have at x equals 9, v equals negative 20 times 9, and that gives me negative 180 pounds. At x equals 9, m equals negative 10 times 9 squared, and that gives me negative 810 pound-feet. Okay, so those are the two extremes that describe moment. Come back to this drawing. I know at x equals 0, v equals 0, so we go straight to right here. At x equals 0, v equals 0. And then at x equals 0, m equals 0, which is right here as well. Alright, so then the next extreme, at x equals 9, v equals negative 180. So if you look back up here, we have, at 9, we have negative 180. So we're going to go down to here. We have negative 180. Obviously, if you're starting from 0 and you want to get to 180, the only option is to draw a straight line between the two of them. Okay. You're going from 0 to negative 810, which is going to be somewhere here. Now the trick is this. If you have a triangular line for shear, your actual moment is going to be a curve. Okay, so we're going to go, it's going to be a curve. So this is linear. This will be a quadratic curve for moment. Alright, that's not, I mean, it is important for what we're trying to do. Alright, so we're done with that. We're going straight to the next section, which for part B, we are starting from 9 and we are going to 21. So at x equals 9, v equals 147.5 pounds. And I'm sure you're wondering, like, how do we even deal with something like that? Just means that there's a discontinuity. So one side of 9, it's negative 180, but the other side is actually 147.5. We're going to move it back up to 147.5. Okay, so then there will just be a drop line. To check your work, just try negative 180 plus 327 and you will get 147.5. Alright, so back here at x equals 21, since this is not an equation, we still have v equals 147.5 pounds. Okay, so we are staying consistent until we'll get to the next point, which is nice. So we're going to go back here, and that's 147.5 pounds. That just gives you a straight line across. Alright, and then going to moment, at x equals 9, m equals negative 2137.5 plus 147.5 times 9. And that gives me negative 810 pound foot. Okay, so we come back here, we're staying right here. And then at x equals 21, we have m equals negative 2137.5 plus 147.5 times 21. and that gives me 960 pound-foot. We've come back here. We're going to go from 9, which is still negative 810. We're going to go to 960, which will be a straight line because this is a rectangle. So this would be linear. And that's going to be 960. Alright, we're almost done. So the next one, we're going to go to cut C. So at x equals 21 feet, v equals 22.5 pounds, and at x equals the other extreme, 33 feet, v equals 22.5, right? Because there's no x involved here. So going back to the drawing, we're going to go at 21, we're going to go down to 22.5, and then at 33, 22.5. Okay, perfect. And then let's worry about m. At x equals 21 feet, m is equal to 427.5 plus 22.5 times 21. And that gives me my m equals 960 pound-foot. Perfect. And then at x equals 33, m equals 427.5 plus 22.5 times 33. And that gives me my m of 1230 pound-feet. And 1 pound-feet. So I have 960. I'm going to go to 1230 pound-feet. And once again, it's a line because this side is a straight line. Then finally, looking at this side, at v from 33 to 45 is negative 102.5. So just a quick drop down. You're going to go with, you're going all the way down here. And I'm sorry about that. It looks like it's going to overlap a little, but it's not that bad. Going to negative 102.5. And then you see 102.5 just pops it right back up to 0. So we're basically done with our shear diagram. And then for the other side, at x equals 33 feet, I end up with my moment at 1230. And at x equals 45, my moment equation, actually plugging in 45 over here, gives me 0. Which is very nice because it looks like we've rounded things up really nicely. So 1230, and then we're going to go all the way down to 0. And that's also a line, linear. Okay. Let me zoom in a little bit. So as a quick recap, if you want to draw a shear moment diagrams, as I said before, there are two ways to approach this, using the method of sections and using the graphical method. Now, for this lesson, what we were trying to cover, we're using the method of sections, which gives us the same exact answer as using the graphical method. What you want to do is make cuts for each discontinuity. So before and after every concentrated load, right? And usually after every distributed load as well, but this covers it. So before the reaction, we made a cut at A. After the reaction, we made a cut at B. After the first 125, cut at C. After the second 125, cut at D. And that's before the reaction 102.5. Once you've done that, what you want to do is do all the work that we've done over here on the side. You're going to make cuts. You're going to take left-hand side or right-hand side of every single cut. Remember to be consistent. If your X is starting from the left-hand side moving towards the last edge, which is your 102.5 reaction, keep that consistent every single time, whether you pick the left hand side or the right hand side. And that's going to play a lot into the last part where we pick the actually the right hand side of cut D, which gives us, if you're making the cut, the entire length minus X, and that's important. Once you do that, it's just summing forces in the Y direction, summing moment, whether the cut side or then the other side, it doesn't matter. Once you have your equations in terms of X, think about your boundary conditions. Where is your moment equation trying to describe? For this part, we're describing everything after 33 feet to the end, which gives us 4612.5 for the moment minus 102.5 times X. So then you see my boundary conditions are at X equals 33 and then at X equals 45. Once you're done with that, plug in those values, come here and draw each one of them one at a time, and that should be a quick, easy way to be able to describe what's going on in the member in terms of shear and moment.